Hi folks, thanks for tuning in to another honors geometry video. This time around I'm going to blow your minds with something brand new called the Pythagorean Theorem. No, we use this all the time. But what this lesson is going to do to expand upon that is maybe look at how it compares to things like, or how it relates to things that we just talked about, like similarity. We'll also kind of look at it in terms of its converse, and what that's going to allow us to do in conjunction with some other logical deductions that we can make is kind of relate the sides of a triangle, specifically right triangles, together with some formulas. So for starters, let's actually define the Pythagorean theorem in terms of an if-then statement, because spoiler, we're going to be taking the converse later, so it's useful to do this. The Pythagorean theorem states, of course you know this, if a triangle is right, then a squared plus b squared equals c squared, specifically when a and b are the legs and c is the hypotenuse. So one thing that we could do is we could look at the Pythagorean theorem through the lens of similarity. And if I want to show that, for instance, definitely not drawn to scale, but if I have like a 15, 20, 25 unit triangle, one thing I could do is I can note that this is basically a scaled up version of this bottom one. It's 3, 4, 5, but with multiples of 5. So if I wanted to therefore deduce that this thing is a right triangle also, I could do so by noting that these things are similar, and if they're similar, then all the corresponding angle pairs would be congruent. So this angle would be right too. So what similarity tells us is basically that every Pythagorean triple could be multiplied by something, and that pretty much every triangle, every right triangle that has side lengths with a common factor can be boiled down to some Pythagorean triple, like a 3, 4, 5, or like a 5, 12, 13, one of those other neat ones that we have. So for starters, we know that these are similar, by the way, due to specifically SSS similarity. We also need to kind of note now that when I say SSS, because that's a thing for congruence or similarity, that we're talking about similarity here. So in terms of actually using this, a lot of times we use the Pythagorean theorem if we have a shape, some polygon, where we can drop an altitude and create a right triangle, even if that means creating right triangles inside of other non-right triangles, like this isosceles one. If I want to find the area of this, what we should be trying to do is find all the ingredients necessary to plug into the area formula, which for a triangle is 1/2 base times height. By the way, pause this if you want to try it. It might be some mental math for you even, who knows. Where we can say 10 is the base and the height is h, but we don't know what it is. The tricky part here, I think, is acknowledging that we could do some Pythagorean theorem stuff, perhaps, but even then we need the ingredients. We can deduce that this angle right here is right. What maybe isn't super obvious is acknowledging that this left triangle and the rightmost triangle, the two halves of the thing, are congruent. This is only going to be the case when the triangle is isosceles, by the way, because I could say that these are congruent via HL. These are both 13. This is congruent to itself. We got right angles, so ta-da! Hypotenuse leg says that these two triangles are congruent. That is particularly useful for us because what it allows us to do is break this base up into 5 and 5. Then what I could do, I suppose, is look at either half of these, and I could say that that half is going to be a right triangle, so the Pythagorean theorem applies. I feel like people usually solve for the hypotenuse, so they're used to doing like, maybe some people in your heads are thinking like 5 squared plus 13 squared equals h squared. Be careful. The variable isn't always going to be the hypotenuse. Like in this case, it's the bigger of the two legs. So I could set this up like 5 squared plus h squared equals 13 squared. Writing with a mouse is hard, so I'll just skip to the answer here. This is 25. This is 169. So if you subtract 25 from that and then square root, you get that h is 12. The old 5, 12, 13 that I was talking about. So great, with the knowledge that this is 12, I now have the height of this thing. So as far as the area goes, 1/2. Even though we used 5 for our Pythagorean theorem, the base is still 10. So 1/2 base times height is 1/2 10 times 12, which is 1/2 of 120, which is 60. Since the units were the same, I haven't included them this whole time, but now it's worth noting that I had 10 meters times 12 meters. Meters times meters is meters squared. Easy. Something that's maybe not so easy. It's acknowledging that there are sometimes going to be restrictions on the values that a triangle's sides can have. So I'm going to pull something else up for this. What I want to note is that some people in the past, I haven't held this against you because how would you know? You would make something like, actually let me go back to this. You'd make something like, and you'd try to draw like, I don't know, like this, like a 2, 2, 4 triangle. Obviously wouldn't look as equilateral as this, and people probably tried to make this bottom side longer. But you know what? This is actually a triangle that cannot exist. This is impossible. It's obviously not drawn to scale right now, but if we did try to draw it to scale, we could see why. And in terms of why that is, let's look at something that's actually moving with moving parts to kind of figure out why. So what I have in this program that I've made is a side length of A that is fixed no matter what at 9. Same thing with B, which is fixed at 15. And C, the length of the largest side, don't call it a hypotenuse, just the largest side, is going to depend on the rest of them. So obviously it approaches the longest value that it could possibly approach, the more obtuse this thing gets, and the closer that angle, closer that angle C gets to 180 degrees. And it looks like it's approaching 24. So, think about how 9 and 15 relate to 24. If I think about the smallest value that side C can have, it looks like about 6. We're rounding here to the hundredths place, but you can imagine it's about 6. And you can think about how that relates to the 15 and the 9, can't you? And even with the visual parts, we can kind of see that the longest side can really only ever be as long as the sum of the other two, because if it were any longer than that, then all the vertices wouldn't actually touch. Some segments, or at least one of the segments, would be too long. The other ones would just kind of dangle without actually meeting anywhere. Same thing if I considered it the other way. It could only really be between the difference of these two things. And there's a name for this theorem. It's called the triangle inequality theorem, and says that any side of a triangle is greater than the difference and less than the sum of the other two. So again, C can only ever be greater than the difference, so greater than 6, but less than the sum, which is 24, of the other two. So if I have two triangle side lengths with their values being 9 and 15, if I don't know the third value, there's not too much I could do with it, but I could deduce that it's going to be somewhere between 6 and 24, which is not a totally useless fact. But let's get this down. Any side must be between the sum and difference of the other two sides. So if I want to put this in terms of an inequality, here we go. I'm just picking C randomly. I could also have it be with A as well in the middle, and say that A has to be less than B plus C, or C plus B, pardon me, and it has to be greater than this quantity, which I could call C minus B. Also notice how I have the absolute values here. Also notice how I only have it on one side of the inequality. That's because if I'm taking a sum of two positive things, which side lengths are always going to be positive, then I don't need to take the absolute values of them. They're going to come out to be a positive quantity no matter what. However, if I'm taking the difference of two things, when one is bigger than the other, it might potentially yield a negative value. So for instance here, if I had thrown these in the inequality and gotten like 9 minus 15 is greater than negative 6. Technically, yeah, my third side length is going to be greater than negative 6, but really I can go even further and say that it's going to be greater than positive 6 as well. Remember that this is just an approximation, so it's not exactly 6. It rounds. So that is why the absolute values are necessary when we're taking the difference, but only on the one side. So I've seen before very rare instances where it helps to break up the three-parted inequality into three separate pieces, like this. And this is just another representation of the same thing. Before I cruise onwards, I want to note one more thing, which is that this very particular layout of triangle sides and vertices is going to become familiar to us, I think, or it should, which is the notion of if I have vertices A, B, and C, those points are going to be capital letters, and then the sides opposite them are going to be the lowercase version of the same thing. So the side length opposite point A is little a, the side opposite point C is little c, and so on. All right, in terms of actually like figuring stuff out and using the Pythagorean theorem, like I said, let's consider a situation like this. After the last horrendous blizzard that we had, little Easter egg to anyone who figures out that logo, a local energy department wanted to determine whether or not a telephone pole had become dislodged and crooked, just because of the weather. You know how it is sometimes. Given these measurements, determine if it is still completely vertical. Completely vertical would imply a right angle here. So really we should be asking ourselves, is this a right triangle? Or is it a non-right triangle? This might require us to make some assumptions here, and I mean I already kind of told you. But we know that the Pythagorean theorem applies when a triangle is right. However, it is also the case that a triangle will be right if and only if the Pythagorean theorem applies. So no longer do we only have this as a tool that tells us or allows us to solve for sides in a right triangle, but we could actually test the Pythagorean theorem. And if it comes out true, then that would imply that we have a right triangle. And if it's not true, then I guess we don't. So let's figure this out. Let's see if 44 squared plus 50 squared is equal to 65 squared. I'm going to throw a question mark here. I absolutely should have done this before, but let's see. 44 squared is 1,936. 50 squared, if I add them together, okay, this is 4,436. And 65 squared is 4,225. Ooh. What this implies is that no, this is not a right triangle. Not right. And if it's not a right triangle, then that means that the pole is no longer vertical. Because we are assuming here that the ground is horizontal, or whatever, however close to it we can get. So no, this is not a right angle that we have here. This triangle is not right, and that means that it has been dislodged. So in terms of still being completely vertical, the answer is nope. And in fact, what we're going to talk about in a moment is a little bit stronger of a statement. We can say not only that this is not a right triangle, but we can go a little bit further and conclude whether it is obtuse or acute. Because if it's not right, then it's one of those two things. So let's try to think. Actually, let's stay here for a second. Let's try to think of how these sides relate to each other. And maybe we could see just based on like the way the image is laid out here. Like try not to make any assumptions based on the diagram. It's not drawn to scale. But consider this. It looks like if this side, let's call it not 65. Let's talk hypothetically for a second. Let's call it C. If C squared did come out to 4,436, then we would have a right triangle, right? Because A squared plus B squared would equal C squared. But C squared is not 4,436. It's less than that. So imagine C then to be not quite a hypotenuse, but a little bit less than a hypotenuse. If I have this third side being smaller than a hypotenuse, then imagine taking a right triangle, and imagine making this angle not right and curving it in a bit in order for these vertices to touch, in order for segment C to be touching both vertices. Because remember, it's shorter than a hypotenuse, so that would have to be the case in order for all the vertices to touch. If we have that happen, if this right angle ends up being less than 90 degrees, well, that would imply that the triangle is obtuse. Sorry, I said that totally backwards. Acute. Whoops. So let's try to make up some rules for this. Okay, fine. Let's deal with our pal 345 instead. If I have a right triangle, we know this, that the C squared is going to be equal to the A squared plus B squared. But the trick to figuring out if our triangle is going to be obtuse or acute is basically how the longest side, how the third side, how the C, compares to the sum of the other two squares. So in this case, if I have an acute triangle, then my 3 squared plus 4 squared does not equal x squared. In fact, this x is shorter than 5 squared. So I would have a less than sign here. The acute formula, so to speak, is that the third side squared, the largest side squared, is less than the sum of the other two sides squared. Conversely, if, for instance, in an obtuse triangle, y is my largest side, and it is bigger than 5, what that would mean then is that the formally right angle would have to open up a bit, it would have to widen in order for the vertices to touch both ends of segment, both endpoints rather, of segment y. And that would indicate that y squared is greater than 3 squared plus 4 squared. To generalize that, we could say c squared must be greater than a squared plus b squared. Don't get yourself into the habit of like seeing patterns that aren't really there. Like if I set up an inequality, a less than implies it's going to be acute, because I could also set up the inequality this way too. I can say a squared plus b squared is greater than c squared, and that's true for acute triangles. Basically, I'm just taking these inequalities and I'm flipping the sides of it. That's a thing we could do. That would reverse the signs. It's just another way of writing the same thing. But really conceptualize what's happening when we compare the a squared plus b squared to the third side. Notice also how I'm refusing to call the third side the hypotenuse. Remember, c is just the longest side here. Hypotenuse is a term explicitly reserved for right triangles, which maybe we don't know if we're dealing with them until we end up using this method right here. Which, speaking of which, this is the final part of this video, so I'm going to dive into some practice problems here. I would very much suggest that you folks maybe pause it and try to classify these triangles, or potential triangles maybe I should say, using the methods that we talked about earlier in this video. So pause now, and I'm going to continue. So, let's see. I wrote all these numbers down, so I wouldn't have to do it right now. But the thing to test, in terms of our sides here, 14 is obviously the largest side, so that would be our C. And then it really doesn't matter how I label these, but I might as well go in order, right? So let's say A and B and C. So what I really want to do is compare how 7 squared plus 9 squared compares to 14 squared. Well, I'll tell you right now, 7 squared plus 9 squared is 130, and 14 squared is 196. So it looks like the 14 is bigger than a hypotenuse, because if it was equal to 130, then it would be a hypotenuse, the triangle would be right, we'd be happy about it. But right now, because it's bigger than that, it looks like something larger than a hypotenuse would only show up in an obtuse triangle. You could probably imagine going to do one of each of these, but who actually knows? In this case, I would do something very similar. This is not the same shade of green. That bothers me. 7 squared plus 23 squared, and see how that compares to 24. Who knows? Take out your calculator, folks. We end up getting that 578, which is the a squared plus b squared, is greater than the other side, which is 576. Which tells me that because the sum of the other two square sides was bigger than 24 squared, the larger side squared, that tells me that 24 is not quite a hypotenuse. It's a little bit shorter than that. And if the biggest side is shorter than a hypotenuse, that would have to imply that the triangle is acute. So take a second to look at the third one, because it's actually tricky. And if you're going through this lesson and you tried this one, what you may have gotten if you got it wrong is that it is obtuse. Because 3 squared plus 4 squared is less than 8 squared. That's true, but that's only true if these sides make up a triangle in the first place, which, guess what, they don't. If I take any of these sides, for instance, maybe like 8, and I want to test, is it greater than the difference of the other two? It is greater than 4 minus 3, which is 1. That's accurate. Is it less than the sum of the other two? It is not, because 8 is not less than 7. So these side lengths don't even make up a triangle. And if you try to think about why that is, if you try to paint a visual in your head, imagine I have like a stick or whatever that's 8 inches long, and then I have another segment that's like 4 inches long, and then I have a third segment that's like 3 inches long. It's going to be a case that the 8 is too long, and then the 4 and the 3 won't actually be able to meet at a vertex, which would tell us that this is not an obtuse triangle. This is not a triangle at all. So let's take note of that. Not a triangle. And the last one right here, if you're having a hard time setting this one up, it may be because you're not sure which one should be considered the larger side. It's not, obviously it's not 8. It's not super obvious which is bigger, 12 or 4 root 13. So what I would suggest is throw 4 root 13 in your calculator, try to figure out what it is as a decimal, and it ends up being something like 14.42, and then you can deduce that this must be the largest side. So let's call this C. So again, the thing to set up here is 8 squared plus 12 squared, and see how it compares to 4 root 13 squared. This may be your first time squaring a radical before. So when you do it, make sure that you actually square the entire quantity, because if you just type it in a calculator without parentheses, you may just be squaring the root 13 and not squaring the 4. But what I end up getting here is 64 plus 144 is 208. What I end up getting here, I'll just tell you it's equal. This is 4 squared is 16. Root 13 squared is 13. 16 times 13 is also 208. So because of this, that tells me that this triangle, whose components satisfy the Pythagorean theorem, is right. So again, to recap, it was obtuse, acute, not a triangle at all, and then right. That should do it. So by the next time I see you, make sure that you're cozy using this whole process to determine if a triangle is acute, obtuse, or right. Again, it's really just using the Pythagorean theorem, except using our assumptions backwards. The if and the thens are flipped. And then also there's this whole thing about figuring out if 3 side lengths are going to make a triangle at all. It was a little bit obvious to me in this case, because it was very clear to see that 4 and 3 are not do not sum up to 8, but it might be less obvious in the future. But that should do it. Thank you for tuning in, folks.